So what I want to talk about are the specific building blocks that create quadratic functions. So quadratic functions stem from multiplying two linear factors. And by linear, I'm going to say x to the first, right? Thus, a quadratic can have up to or as many as two x-intercepts. It cannot have more. It can have less, as you'll see moving forward. The graphs of quadratic functions are always, or let's say nonlinear here. Nonlinear in that they do not produce straight lines, and the curvy shape they produce is called a parabola, which you should have heard about in Math 1. All right, so let's talk briefly about some specific parts of quadratic functions or features. X-intercepts, the places where the parabola, and we're going to use two words here, crosses or touches, of course, the x-axis. That should not be new information. The places where the parabola crosses or touches the x-axis. It has a few other words associated, so zeros are another word. Zeros, aka roots. So anytime you hear me say one of those three words, I mean the same thing. The x-intercepts are the zeros, the roots, the places where the parabola crosses the x-axis. So let's take a look at, let's just draw some random one, and we'll talk about what are those. That's actually what these locations are, right? So make sure you see, hey, there's two of them there for that particular graph. That graph has two. And like we said, it's possible for a parabola to have two. It might just have one. What you'll see also, if you shift this parabola up to a certain degree, it is possible that the parabola does not have any x-intercepts. So just wait until we reintroduce measuring numbers later on. All right. The y-intercept, which is normal in any function, that's the place where, I'm going to use some different f of x, right, where the function crosses or touches, it's going to be crosses generally, crosses the y-axis, and that does not have any different names. All right, so if we draw a specific graph here and take a look, oh, it looks similar. That looks just like the one I just drew. Yeah, well, that's fine. I'm only going to highlight that point, right? That's the y-intercept. So before we move on to the vertex, let's go ahead and take this time to look at particulars of the x-intercepts, particulars of the y. So what we know, they always have the format x, comma, 0. Okay, and that's very important. There's a lot of information in that. X, comma, 0 is implying, actually it's coming and slapping you in the face and saying, hey, the y-coordinate is 0. And make sure you see, hey, yeah, y would be 0 at both of those. Conversely, when you look at the y-intercept, the format will always be 0, y. Okay? And again, all that means is that every y-intercept for any function, regardless of what kind, will always have an x-coordinate of 0. That should not be new information, but if it is, great. All right, so the vertex. If we had to pick a particular point that was more important than any other, I would call it this one. All right, so we're going to say that's the max or min point where the parabola is birthed. All right, now birthed. That's a weird word to use there. I'm not sure why I like to use that word, but I do. And the reason is it's unique in that it does not have a corresponding point. The vertex is either going to be the top or bottom of our parabola. Now, both of these parabolas have a bottom, right? So, hey, why don't we just draw one that has a top instead? We'll call it a maximum. All right, so if we draw a parabola that's open the other way, right? It's open the other way. That's going to have a max. So we'll make sure we highlight that here. Make sure we recognize, hey, that's like the top of a mountain, right? And there's some specific ways we're going to remember how those appear. Why is it open down? Why is it open up? So on and so forth, right? But if I were to locate the vertex on that one, it'd be down here somewhere and down here somewhere for this one, right? I just chose to make sure you see, hey, parabolas can be open up or down in our study of them. Okay, so again, the vertex, the maximum or minimum point where the parabola is birthed. All right, and you see how the arrows extend out from there. Okay, when you study parabolas in pre-cal, you'll notice another maybe reason I chose to use the word birthed. Okay, and just for future reference, let's go ahead and put the letters H, K there. All right, now, those will come in handy later. I'm going to go ahead and just give you the standard forms here. So y equals ax squared plus bx plus c. Hopefully that's not new. You saw that on the Angry Birds activity. And then vertex form, y equals a times x minus h squared plus k. All right, don't worry if that doesn't make a whole lot of sense yet. One thing I definitely want you to pay attention to, though, is the fact that they both have the letter a. So that is not a coincidence. That's going to come into play heavily. All right, so what we need to be able to do first is convert to standard form. So what we have here is two linear factors, as I referenced up here. Linear is in, hey, that's an x to the first and that's an x to the first. You multiply them together, you get a quadratic expression or equation, or in our case, a function. So we're going to be able to graph it. So what we've got to do is use the FOIL method or distributive property or the box method, whatever it is that you like to use. And what we're going to do, we're going to say, we're going to rewrite it. Again, it's equal x squared plus x minus 6. Make sure you can get that standard form. Okay? That's going to highlight a few things for us. Okay? And what I want to focus on for this first example is just one of those highlights. That will be, hey, let's bring a highlighter in. That will be the significance of this number here. All right? What is the significance of that? Well, I want you to think about something. X can be any number. That's why we call it a variable. So the 6 does not have an x. And this is generally what a lot of students point out. Therefore, I recognize that to be the constant term, as in it doesn't change. It's always going to be a 6. X and x squared and x, those can take on different values, right? Depending on what you plug in for x. But 6 is always there. So what happens at a particular value, x equals 0? What ends up happening is y equals negative 6. Now, that's important to remember to go back to the y-intercept. The format's always 0, comma y. So if I were to plug in 0 for this particular equation for x, I'd get negative 6. What does that mean for us? That we're going to be able to come over here and say, for our graph, that 0, negative 6 is on the graph. Right? That's going to be our y-intercept. So what did we have to do to reveal that to ourselves? We had to convert to standard form to show us. So the C is the y-intercept, if you will. You only get that from standard form. We can't just look at the numbers in the factored form and get that. We've got to get that from the standard form. Okay, now some of you will be able to do that eventually. But all right, so then what we're going to do, let's see. I just know it looks kind of like this, and we'll just go from there. Right? I'm not worried about the other stuff, not at least on this one. Right? So that's 0, negative 6. That's the location of that point. All right, so that's our parabola, right? Make sure you clear on that. I multiplied, I've converted to standard form. It looks kind of like that one at the top. The C value is a negative 6. That is my y-intercept. All right, moving on from there, sketch the graph based on the roots and the quadratic coefficient, also known as the A value. All right, so what we're going to do, I'm not going to multiply here. They didn't ask me to. They want me to sketch the graph based on the roots. What are the roots? The roots, if you go back, are those x-intercept thingies, also known as zeros. Quick question. Why do you think they call them zeros? Because they are the place, or the values, that make the equation equal to 0. So what's happening here, we have three things multiplying. The 3, that's a 3. That doesn't change. That's why we don't call it a variable. But these other two things, they include the x. As you know, x is a variable. So we're able to plug in and think about different values of x that can exist, right? And that's what a function is, a representation of all the combinations of x and y that satisfy a particular equation. All right, so what I've done here, I've set this entire thing equal to 0. So that means, hey, that's y equals 0, right? So if that's true, what we want to think about is the fact that these two things are multiplying. Leave the 3 out for now, it doesn't matter. If I can make either of these 0, then 0 times who cares is still 0. 0 times who cares is still going to be 0, or a true statement. So basically what's going on, guys, if I can make this one 0, I know that I will get this entire equation equals 0, meaning I'll have one of the x-intercepts. So x equals positive 1 is one of the x-intercepts, right? We're going to mark a 1 there. What if I can do it with this one? What if I can do it with this one? If x plus 2 equals 0, that means x equals negative 2 is another place where the y is equal to 0. And we started out saying, hey, this can happen 2 times for these functions. Right? So what I'm doing, I'm using the parentheses, each parentheses, or we'll call these factors, individually, right? I'm working with one at a time. And the reason is, if I can make this 1, 0, if all these are multiplying, 0 times anything, still 0, still a true statement. So if x is negative 2, boom, everything becomes 0 because they're multiplying. If x is positive 1, boom, everything becomes 0 because they're multiplying. All right. From then on, right, we could convert this to standard form. What would be the benefit there? That would actually show us our y-intercept, right? I'm not going to do that. Instead, I'm simply going to look at, I know you can, and we're starting to do that later in class. The fact that both of these are 1 times 1, that's 1 times 3. So my quadratic coefficient, if I go back up here to the standard form, by the time you get done with that, that's going to be a positive 3. And anytime a is greater than 0, our quadratics are going to be open upward. All right. So that's what we're dealing with. A parabola with x-intercepts or zeros at negative 2 and positive 1 that's open up. Right, now if you go through and you multiply all that out and you get the standard form, which I think you should do, we can check that later in class. Let's see what you're going to get. 3x squared plus x. So plus 3x minus 6. Oh, that makes sense because we got a negative y-intercept. Now we know that it's particularly at negative 6. All right, last thing. Let's do this with this one. So this is a little different. These two things, however, are still multiplying, aren't they? So what I want to do is pick out the 2 linear pieces. So there's a linear piece. How do I recognize it? It has x to the first. There's a linear piece. It has x to the first. Similar to the last one, these two things are multiplying. So what I'm going to do is set each of them equal to 0 to help me figure out what their particular solution is. This one's going to be 3. This one, oh, that one's a bit tricky. Negative 4x equals 0. Wait, it's so easy that it's tricky? What can I multiply by negative 4 and get 0? 0. So I have 2 places where this one touches. 0 and positive 3. So I have our, you can tell that's 0, right? The difference here is that this a value is negative. So when a is less than 0, what do you think? It's going to be open down. All right. A couple other things to point out. If you get hung up on this, convert to standard form. So if we write the standard form here, we're going to get negative 4x squared plus 12x. Wait, there's no c. There's no c. There's no number without a variable. So I can just put plus 0. It's like going to the prom by yourself. Here's my plus 0. So we know, hey, the y-intercept is 0. So that backs up our claim that one of the x-intercepts was 0. And we're good to go. All right, so these are just a few introductory tasks that highlight the basic building blocks of quadratic functions. Do these, go over this, watch it again if you have to, and we'll get moving tomorrow.